Question 9 says an alpha particle is projected eastward, parallel to and along the Earth's equator, where the magnitude of the Earth's magnetic field is 5 times 10 to the negative 5 teslas. Based on the information above, that the speed of the alpha particle is 5.5 times 10 to the negative 2. The magnitude of the deflecting force on the alpha particle is. Okay, that's a pretty straightforward question. I'm going to go over that, and then I'm just going to go over a permutation of that question they could have asked to make it a little more interesting. But that one's straightforward because you're given the Earth's magnetic field strength at that point. You're given the velocity. Ooh, the -2 is not exactly cooking. And you're asked to find the deflecting force. Fm equals, and of course you're given what kind of particle it is, therefore you know the mass and the charge. Now we don't need the mass for this question, but we do need the charge of an alpha particle. And then we can just plug them into the formula Fm equals QVB. So we're just multiplying those three numbers together, and that will give you the answer to the C. If I wanted to make that question a little more interesting, I would say something like, what must be the strength of the magnetic field so that the alpha particle is not deflected towards or away from the surface of the Earth? So if the alpha particle is just going to travel straight, kind of along the surface of the Earth or above the surface of the Earth at the same height, what would be the magnetic field strength? And in that case, you would have to say that the magnetic force equals the gravitational force. So you'd have to set two forces equal to one another. And then you'd have to solve it like that, equals mg divided by qb, and you'd solve for what the magnetic field strength is in order to keep the particle at the same level. So that's just, that may be on the final one, it may not, but if I decide to put on the final, then you'll know how to solve it. Okay, number 6, a magnet and two coils. There's a magnet and two coils. Refer to the above diagram. Magnet A is moving at a uniform speed between two solenoids. The magnetic polarities at position A and B respectively are. So this, again, this is a Lenz's law question. And we have a moving magnet. It's near in the presence of conducting wires. And so that moving magnetic field will cause the currents in both of those wires. And that current will induce its own magnetic field. And so you can have a magnetic field here. You can have a magnetic field there, and you just have to decide the north and the south poles. And you always have to think, I need to do work to move this magnet. All right, sorry, I was interrupted, and now I forgot what I was saying, where I was at. So let's just kind of pick it up. And oh yeah, so we've got a magnet moving in between two solenoids. They're both can have magnetic fields. You have to do work. That's where I was. You have to do work to move that magnet. So if you have to do work, then clearly this is going to be a north pole. So you have to do work to overcome the repulsion over here, south pole. And what about here? Is that going to be a north or a south? Well, again, it's something that you have to do work. And if this was a north pole, sorry, if this was a south pole, if that was a south pole, then these two would repel, and that's not doing work. So you have to do work to overcome the attraction in this case, because the magnet, if that says attraction, is moving in that direction, and therefore this must be a north pole and this must be a south. So A is north, B is north. The answer is A. Number 11 is a very simple knowledge question. Electromagnetic radiation listed in the order of increasing energy. So all you have to do is know your radio wave, microwave, infrared, visible light, ultraviolet, X-rays, and gamma rays. And this is increasing frequency. And because of this, oops, because E and F are directly proportional, in other words, as the frequency increases, the energy increases, and this is also an increasing energy. And so which one of those is in the correct order? And that would be D. Microwave, infrared, visible, and X-ray. And a reminder that as you're going that way, this is increasing frequency, but is decreasing wavelength. So the wavelengths get shorter, but the frequency gets higher and the energy gets higher. Number 12, we've got a Michelson question. An observer uses a 10-sided mirror to measure the speed of light. And I'm not even going to attempt to draw a 10-sided mirror. It will be an abomination. A clear image occurs 1/10 of a rotation when the mirror is rotating at 431 revolutions per second. The total path of the light pulse is 60 kilometers, measured from the light source to the mirrors and reflected back to the observer. What is the speed of light calculated from these data? So just a reminder, I'm just going to do a simple octagonal mirror because that will be not quite the abomination of a 10-sided mirror. But just to review, light source goes here, hits this mirror, goes down here, hits another mirror, comes up here, and then goes to the observer right there. So this is the Michelson setup for measuring the speed of light. It's always just going to use your basic formula. V equals D over T. The D we have is 60 kilometers. So that would be 60,000 meters. What we need is the T, and you have to ask yourself, so it says, a clear image occurs every 1/10 of a rotation. So when this mirror ends up over here, that's 1/10 of a, now this is an 8-sided mirror, so you have to pretend this is a 10-sided mirror. So when this makes 1/10 of a rotation, then you see a clear image. And so what you have to ask yourself is you have to say, well, if the mirror is making 431 revolutions, I'm just going to say cycles, per second, how long does it take to do 1/10 of a cycle? This is how I would do it. There are other methods to doing these problems. I'm just going with this one because I like it. And then solve for x. X equals, and you're going to get a very short amount of time. This thing's going around 431 times in a second. So it's spinning really fast. So the time that it takes to do 1/10 of a revolution is going to be very small, and it turns out to be 2.32 times 10 to the negative 4. Seconds. So that's the amount of time that it takes to do 1/10 of a revolution, and then you can plug it into this. And get the answer. Now, of course, if you were just guessing and checking, not guessing and checking, if you were taking just a guess on this, yeah, I mean, that's ridiculous. This is insanely slow. Even that's really slow. So if somebody did this experiment and they got that an answer, you'd say, yeah, go back to school. You're clearly not a great scientist. All righty then, on that negative note, number 13 is a concave mirror with a focal length of 20 centimeters used to observe an image of a 1.75 centimeter candle that is placed 15 centimeters from the mirror. The mirror image is, all right, these problems were always going to start, you don't have to, but with a rough diagram. It's a concave mirror. There's a concave mirror, has a focal length of 20. So if I say that that's 20, then the center is 40, and the object is placed 15 centimeters. So the object is right here. And it doesn't matter, I'm not drawing to obviously size in terms of the 1.5 centimeters, because that's kind of that'll be a little harder to draw. So if we have this configuration, then we can use a ray diagram. And remember for our ray diagrams, if a light ray is parallel, it goes through the focus. And then for this one, since the object is in front of the focus, it's easiest to use the third rule, which is that if it goes through the center, it goes straight. So through the center, it goes straight. And you can see that these lines, I didn't draw that very well, are never going to intersect. In fact, they are going to intersect over here. So this is, and you should know this, you should know that if it's a concave mirror and you put the object between the focal length and the surface in the mirror, then you get a virtual image. All right, now just by drawing that, we can see what the answer is going to be. The only way that it could be impossible to see if the object was on the focal point, or on the focal point, because then the two lines would be parallel and they would never intersect. So it can't be that one. And then B says erect, which means it's right side up, and the other two options are both inverted. So you can automatically get B, which is the correct answer, just from drawing a diagram. Now, if I was writing this question, I would probably not make it so obvious. I'd make it so that you actually have to do the math. So let's do the math in case you get a question where you actually do have to do the math. So the math is going to be, we need to find out the DI, the distance of the image, and we need to find out the HI, the height of the image. So step one is the distance. There's our formula, there's our manipulation. Just be careful about this. 1 over DI is 1 over 20. 15. And you should right away see that you're going to get a negative answer, which you should get a negative answer because the object, if it's a virtual image, you're going to get a negative. Where's my calculator? It's gone. And when you're doing this on your calculator, just be careful. This is the way I do it. I go bracket 1 divided by 20, end of bracket, minus bracket 1 divided by 15, end of bracket, equals. And then I get negative 0.16 repeating, and then I go 1 divided by second function, the minus sign, which is second answer, and it spits out negative 60. DI is negative 60. All right, so, and well, that doesn't clear up the answer for, so it could be B or D. If you didn't draw a diagram, you could say, okay, it could be B or D. Now we need to find out the, oh, look at that. You're gonna have to draw a diagram because one is, the B and D are exactly the same, except for one is inverted and one is erect. So in actual fact, by drawing the diagram, yeah, you can get the answer B, but let's just verify that and get the actual height of the image. And for that, you're going to use, let's do this way. And solve for HI. Oopsie. And then plug those numbers in. Negative 60 times 1.75, sorry, yeah, negative 60. So it becomes positive, which is good because we want the, we know from the diagram that the image is upright, so we should get a positive answer. So when we do this, let's do it actually so it's really clear. what was it? It was 15. So when we do that and we stick it into our calculator, we get positive, notice it's positive 7 centimeters. And so then even if you didn't do a diagram, we know that it's erect because we did array diagram, but even if you did, because you get a positive answer, you know that it must be upright or erect. So that's how you would know it's B without even having to do a diagram. Okay, can we squeeze in one more? Ooh, let's not. Let's do number 14 in the next video.